There are tens of thousands of different chemical compounds that make up our world. Some of these materials are natural. For example, people have used cotton, a plant, for clothing, and flint, a rock, for tools for thousands of years. Other materials are synthetic, invented and produced by people. Nylon and steel have similar functions to cotton and flint, but they are synthetic. In fact, the substance nylon did not even exist before this century. Well, before last century. This book was written last century. Which of the objects in the photograph are made of synthetic substances? How are these substances made? All substances, whether natural or synthetic, are made of the same building blocks, atoms. Atoms can combine to form molecules. Molecules that are made of more than one type of atom are called compounds, and the number of possible compounds is almost infinite. However, there are only 100 different kinds of atoms to use as building blocks. For example, each molecule of acetic acid is made up of atoms of carbon, oxygen, and hydrogen. What makes these three atoms different from each other? Do any other atoms have similar properties to these three? How does it help you when things are organized? In the last century, a scientist called Dmitri Mendeleev looked for ways to organize the current knowledge about atoms. He invented a periodic table, an organized arrangement of elements that explained and predicted physical and chemical properties. Mendeleev's table was the key to understanding elements and discovering new elements and compounds. How did Mendeleev organize his table? Make a list of some of the things that you organize or are organized for you in your daily life. Now, just a note, when it said in the last century, a scientist called Dmitri Mendeleev, it was not the last century, because this book was written in the late 20th century. It was the century before last. This is the 21st century, and he worked on his periodic table in the 19th century. Okay, we're going to do this. It says, try this, organizing elements. Using graph paper or chart paper, cut a strip of paper 20 centimeters long by 1 centimeter wide. Draw vertical lines on the paper to divide it into 20 squares. Write the numbers 1 through 20 consecutively in the squares. See figure 1. The numbers represent 20 elements. Cut the tape into pieces by cutting along the lines between A, elements 1 and 2, B, elements 2 and 3, C, elements 10 and 11, and D, elements 18 and 19. You should now have 5 pieces of paper. You are told that elements 3, 11, 19 have similar physical and chemical properties. Line up these elements in a vertical column and tape the strips of paper into your notebook. The other columns will also line up. Look at the table you have made. Which elements should have similar properties to elements 4? Which element should have similar properties to element 9? Assuming that the elements' numbers are also their atomic numbers, draw Bohr-Rutherford diagrams for elements 3, 11, and 19. What do these elements have in common? Where do you think you should put elements 1 and 2 on your table? Tape them into your table and explain the reason for your choice. Figure 1. Write numbers in order on a piece of tape as described. Organizing the elements. We often organize things to make them more useful. When you bake a cake, for instance, you might think of ingredients in categories. You need something sweet for flavor, fat for bonding, flour for substance, and something to help it rise. Many different ingredients can fall into each category. You can combine ingredients from these 4 categories to make different kinds of cakes. Up to the mid-1800s, scientists were busy discovering elements and recording their properties. Then they tried to organize their experimental observations in a useful way. At first, they listed the elements alphabetically, but each time a new element was discovered, the whole list had to be changed. They tried other organizing methods. Could elements be grouped by state and color? No, too many elements look alike. By taste? Definitely not. Too many elements are poisonous. Also, taste, color, and state cannot be measured. The scientists also used properties that you studied earlier in this unit. For example, properties such as conductivity, malleability, and luster suggested that elements could be grouped generally into metals and nonmetals. Figure 1. Physical and chemical properties suggest that elements can be organized into metals and nonmetals. John Dalton and other scientists found a quantity that could be measured for an element, its atomic mass. The atomic mass is the average mass of an atom, that is, of all occurring isotopes of an element. Each element has its own unique atomic mass. Several scientists started to arrange the known elements according to their atomic masses. Figure 2. One early scientist organized elements in an arrangement that looked like a coiled spring. Mendeleev and the first periodic table. The best arrangement of elements was produced by a Russian scientist, Dmitry Mendeleev, in Figure 3. Working with the 64 known elements, he wrote the name of each element on a separate card along with its atomic mass and other properties such as solubility, density, flammability, and so on. Then he played chemical solitaire, arranging the cards in different ways to see if he could find any patterns. Perhaps a pattern would explain the behavior of the known elements. He also hoped this might show a way to discover new elements. Mendeleev organized his first periodic table by arranging the elements in order of increasing atomic mass. When an element or group of elements seemed to repeat properties he had seen before, he started a new row. Eventually, he found that elements with similar properties fit into the same vertical column. However, often an element seemed to belong in a place based on its mass, but did not fit based on its properties. When that happened, he ignored the mass and moved the element to a column with other elements having similar properties. Mendeleev's arrangement showed a regular pattern, which he described as a law. Simply put, a scientific law is a rule that nature appears to follow. It is a generalization of many Observations, a statement rather than an explanation. Mendeleev's periodic law states, if the elements are arranged according to their atomic mass, a pattern can be seen in which similar properties occur regularly. Let's just look at Table 1 for a moment. It says, two of Mendeleev's predicted elements, gallium and germanium. It was predicted in 1871, that's gallium, and it was discovered in 1875. And you can see that the atomic masses were very close, possibly exactly relative to the mass number, but the average was quite different. And then the germanium was predicted in 1871 and discovered in 1886. And the atomic masses were very similar. And also the predicted properties were very, very similar to what they were discovered to be. Understanding concepts. What are some of the properties that help scientists organize elements into metals and nonmetals? 2A. What property of atoms did Mendeleev use to organize elements? B. How did he use this property to organize them? C. When did he ignore this property in building his table? 3. Examine the elements in the first column of Mendeleev's first periodic table. All but one are shiny metals. What is the exception? B. The first four elements in this group have atomic numbers 1, 3, 11, and 19, respectively. What do these elements have in common? Number 4, examine the first two columns of Mendeleev's periodic table. Refer to Table 2 on page 64. 4A. What are the combining capacities of the two elements from the first column? B. What are the combining capacities of the three elements from the second column? C. What does this suggest about the combining capacities of all the elements in Mendeleev's periodic table? And 5, sodium chloride, potassium chloride, and calcium chloride are all used for melting ice in the winter. The chemical formula of sodium chloride is NaCl. I think it's going to say predict the formulas for potassium chloride and calcium chloride. It doesn't appear to finish, it seems to be cut off. So let's assume that they're saying the last sentence is predict the formulas for potassium chloride and calcium chloride. Exploring the modern periodic table. Mendeleev's periodic table was a major breakthrough in the understanding of the elements. However, he found that organizing elements in order of atomic mass did not always work. In some instances, he had to decide whether to place an element by its atomic mass or by its properties. He concluded that his calculation of atomic mass was flawed, trusted his instincts, and went with the properties. This decision proved to be a good one when the nuclear atom subatomic particles were discovered. People realized that the key to the identity of an element was the number of protons in the nucleus, the atomic number rather than the atomic mass. A new law was born. The modern periodic law states, If the elements are arranged according to their atomic number, a pattern can be seen in which similar properties occur regularly. These properties include melting and boiling temperatures and the sizes of atoms. The size of a spherical atom is called the atomic radius, the distance from the nucleus to the outer edge of the atom. In the nuts and bolts activities, you organize the hardware items and look for trends in properties such as length and mass, both along a row and down a column. What trends in properties can we observe when we organize elements into a periodic table by atomic number? How does the arrangement of elements in the periodic table relate to the arrangement of electrons in the atoms? Work in pairs and refer to the periodic table on the inside back cover to answer these questions. Procedure 1. Examine the periodic table on the inside back cover. Note whether the elements are solids, liquids, or gases at room temperature. A. Which symbols represent elements that are gases at room temperature? Name 2 elements that are liquid at room temperature. 2. Look at the symbols and atomic numbers of the elements. A. What is the atomic number of helium? What is the atomic number of gold? What is the symbol of the element with the atomic number 22? What is the symbol of the element with the atomic number 33? Number 3. Look at the atomic masses of the elements. What is the atomic mass of aluminum? What is the atomic mass of silver? What is the symbol of the element with the atomic mass of 40.1? What is the symbol of the element with the atomic mass of 83.8? 4. Mendeleev used atomic masses to organize his periodic table. What 2 elements are out of order according to atomic mass in the 5th row? Number 5. Look at the densities and melting points of the elements. Which element has the highest melting temperature? Which element has the lowest melting temperature? Which element has the greatest density? Which element has the lowest density? Elements 1, 3, 11, and 19 are in the first column of the periodic table. Draw board diagrams for these elements. How is the electron arrangement in these elements similar? How many electrons do you think there are in the outer orbit of these elements? Rubidium and cesium. 7. Elements 9 and 17 are in the second to last column of the periodic table. A. Draw board diagrams for these elements. B. How is the electron arrangement in these elements similar? And C. How many electrons do you think there are in the outer orbit of elements bromine and iodine? Look at elements 3 to 10. Draw board diagrams for these elements. B. Describe the general pattern that you observe across a row of the periodic table. Elements in the same column tend to form similar compounds. For example, the compounds that hydrogen forms with elements in the first column are lithium hydride, sodium hydride, potassium hydride, and rubidium hydride. The compounds that hydrogen forms with elements in the second column are beryllium hydride, magnesium hydride, calcium hydride, and so on. Hydrogen forms the following compounds by combining with other elements: methane, ammonia, water, and hydrogen fluoride. A. What are the formulas of the compounds formed by the combination of hydrogen with the following: silicon, phosphorus, and sulfur? Understanding concepts. In what state are most elements at room temperature? Illustrate how the following properties generally change as you go from left to right in the periodic table: atomic number, melting temperature, atomic radius. Number 3, illustrate how the following properties generally change as you go down the columns of the periodic table: density, melting temperature, and atomic radius. Look at the portion of the periodic table in Figure 1. Facts about calcium have been omitted. Use your understanding of the periodic table to predict the properties of calcium. Number 5. A. Plot a graph of atomic radius versus atomic number for the first 20 elements. B. What general trends do you observe in your graph? Making connections. 6. Elements in the same group have similar properties. Think of 2 examples in everyday life where similar substances could be substituted for each other. What other factors would you consider before making the substitutions? Groups of elements. When you go to the supermarket, how do you find the foods on your shopping list? If you are looking for yogurt or milk, you look for the aisle marked dairy products. For potatoes or carrots, you look for the fruits and vegetable aisle. Food in a supermarket is arranged so that people can find things quickly and easily. In the same way, the periodic table groups elements with similar properties. You can quickly identify an element as a metal if it is on the left or in the center of the table. Nonmetals are generally found on the right side. The set of elements in the same column in the table is called a chemical group. These elements have similar physical and chemical properties. They form similar kinds of compounds when they combine with other elements, and their behavior can be explained by the Bohr-Rutherford model of the atom. The elements in a group have the same number of electrons in the outer orbit and tend to form ions by gaining or losing the same number of electrons. The table above, the alkali metals all form a positive 1 charge. The alkali earth metals all form a positive 2 charge. The boron family +3. The carbon family either +4 or -4. The nitrogen family all -3. The oxygen family -2. The halogens -1. And the noble gases do not form a charge. However, the transition metals and the intertransition metals, the rare earth metals, they have multiple oxidation numbers. They form multiple charges. For instance, iron will form a +2 or a +3. Copper will form a +1 or +2. Chromium, cobalt, they all have multiple oxidation states. They form multiple ion charges. According to the numbering of the columns above, groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, they all form one charge, as I indicated earlier. But the transition metals and the intertransition metals, the rare earth metals, they have multiple oxidation states. Noble gases. The elements that occupy the far right column of the periodic table, figure 1, are the noble gases. All gases at room temperature, the noble gases, are often called inert gases because they are so unreactive, almost never forming chemical compounds with other elements. You might think that such elements would be rare, but argon makes up almost 1% of every breath of air that you inhale. Because it is colorless, odorless, tasteless, and non-reactive, no one notices it. Their lack of reactivity makes noble gases quite useful. Figure 2. Noble gases have many applications. Helium gas has very low density and is used in lighter-than-air blimps. Neon is used in colorful light displays. Argon is used to fill light bulbs. If ordinary air were used, the filament would catch fire and burn out in seconds. The lack of reactivity of noble gases is explained by their electronic structure. Chemists describe their outer orbits, shown in figure 3. Noble gas atoms do not react with other atoms because they already have a stable arrangement of electrons, alkali metals. The elements that occupy the far left column of the periodic table, figure 1, are called the alkali metals. Lithium, sodium, potassium, etc. are all shiny, silvery metals. Unlike the noble gases, they are extremely reactive, figure 4. Like all alkali metals, sodium reacts vigorously with water. The reaction releases heat and produces pure hydrogen gas. Why could this reaction be dangerous? Because they combine so readily with other elements, they are found in nature only as compounds. Alkali metal compounds are found everywhere on Earth. Figure 5. Alkali metal forms compounds such as sodium chloride, salt, sodium bicarbonate, baking soda. If potassium bitartrate is added to baking soda, baking powder is formed. The most common are sodium compounds, which occur in plants, animals, soil, and seawater. Do you remember the chemical name for salt? Another compound, sodium hydroxide, is used in making soap and paper. It's called lye. That's the old name for it. Potassium and sodium compounds transmit nerve impulses in your body. Part of the experimental proof that alkali metals are in a group is given by the formulas of the compounds they form. Lithium hydride, sodium hydride, and potassium hydride with hydrogen. Lithium oxide, Li2O, sodium oxide, Na2O, and K2O, potassium oxide, when they react with oxygen, and so on. They clearly have a lot in common. The reactivity of the alkali metals is explained by their electronic structure. The outer orbits, figure 6, have one electron, an unstable arrangement. So alkali metals tend to lose this electron, becoming ions with a charge of +1. These ions readily join with other elements such as oxygen and chlorine? Well, if you look at the periodic table, say sodium has 11 electrons and 11 protons. So its nearest noble gas is neon. So it's going to lose one because it wants a valence shell. It wants an outer shell just like neon. It's not going to be neon because it's still going to have 11 protons, but it's going to look like neon from the outside because it's going to have 10 electrons in the valence shell, just like neon. It actually has 8 electrons in the valence shell. I apologize, but it will have 10 total electrons, just like neon. And it will have 8 electrons in the valence shell, just like neon, and it will be unreactive as well. Halogens. Fluorine, chlorine, bromine, and the other halogens that occupy the 17th column of the periodic table next to noble gases, figure 1, are the most reactive nonmetals. Because of their reactivity, they almost always appear naturally as compounds, not as elements. The pure elements you may see in your lab are artificially extracted. For example, chlorine is extracted from seawater by electrolysis. As shown in the periodic table, on the inside back cover, the halogens occur in different states. Fluorine and chlorine are gases at room temperature, bromine is a liquid, and iodine is a solid, all at room temperature. The reactivity of halogens makes them very useful. The most common halogen compounds are chlorine compounds found in living things, seawater, and rocks. Table salt is mostly sodium chloride. Well, it's all sodium chloride, but is iodized by adding a small amount of potassium iodide to prevent disease of the thyroid gland. Chlorine is used to kill bacteria and purify drinking water, but in large amounts it is extremely dangerous. Figure 7. A train derailment involving tank cars containing chlorine gas forced the evacuation of the city in Ontario in 1979. I am not even going to try and pronounce the name of that city. Iodine is dissolved in alcohol to make an antiseptic to treat skin cuts. Sodium fluoride is added to toothpaste because the fluorine atoms bond to tooth enamel, making it less likely to develop cavities. Halogens are so reactive because of their electronic structure. The outer orbits of the fluorine and chlorine atoms, figure 8, have 7 electrons. They just need 1 to be like a noble gas. In chemical changes, halogens tend to gain 1 electron in order to have a stable arrangement of electrons. They want to be like a noble gas. That's the whole point. Halogen ions have a charge of -1 and a valence shell like the succeeding noble gas. A group of 1. Hydrogen is a unique element. Its most common isotope has only a single proton, no neutron, in its nucleus. Like the alkali metals, it has only 1 electron in its outer orbit. Losing the electron makes the hydrogen ion positive, so it reacts with other elements, such as the halogens, that need extra electrons to fill their orbits, resulting in negative ions. Hydrogen has little else in common with the alkali metals. It is a colorless, odorless, tasteless, highly flammable gas, figure 9. Hydrogen's low density makes it useful for weather balloons. Why is hydrogen not used in blimps that carry people? The Hindenburg crashed in Lakehurst, New Jersey, not far from where I grew up, was born and raised. Terrible, 1930s. In other reactions, hydrogen acts like a non-metal, gaining one electron, so it has a complete first orbit. For example, it reacts with alkali metals to form compounds such as lithium hydride, sodium hydride, potassium hydride, and so on. Almost all of Earth's hydrogen exists in combination with other elements. Its reactivity is too great for it to exist in the atmosphere as a free element. Hydrogen is one of the main elements in all living things, as well as in petroleum, coal, and natural gas.